Think forward. Think Research Channel.
The opinions expressed in the following program are strictly those of the speaker. They do not necessarily reflect the views of the National Science Foundation.
From the National Science Foundation, where discoveries begin. This is Frontier. Discussions of today's most exciting research subjects by distinguished scientists and engineers working at the frontiers of knowledge.
Hi, this is Jerry Beilinson for Popular Mechanics Magazine, and we're here in Arlington, Virginia with the National Science Foundation, our partners in today's conference, which we're calling Bridges to the Future. And what we want to talk about today are challenges facing infrastructure in the United States in the 21st century. And just as importantly, of course, we want to talk about solutions and smart technologies to help meet those challenges. We're starting with a conversation on the electrical grid and specifically on the smart grid concept. First, I'd like to introduce, though, our panelists. Joining me in the studio is Dr. James Momo, Director of the Center for Energy Systems and Control at Howard University in Washington, D.C. Also here in the studio is Roger N. Anderson, the Director of the Edison Program at the Center for Computational Learning Systems at Columbia University in New York City. And joining us remotely is Dr. Anjan Bose, Distinguished Professor of Electric Power Engineering at Washington State University in Pullman, Washington. Welcome, Dr. Bose. Thank you all for being here. Dr. Momo, the United States suffered in 2003 a significant blackout on the East Coast that shut down a big portion of the country. There was another blackout in 2006 in California that was blamed for 141 deaths. And there have been smaller power outages throughout the country. So I guess the first question is, are we in trouble in the United States with our electrical system? And are we, in fact, facing a crisis at some time in the future?
Thank you, Jerry. It is my pleasure to be a part of this panel. Indeed, the electric power grid, as we know it today, is the hub of our economy. It's that which generates all the resources, either from all the stakeholders, whether it be manufacturing, whether it be industry, whether it be commercial. It has served its time over the years, and it continues to be. But it's faced with many challenges as we know it. First of all, let's look at the grid coming from the generation side of the business, all the way from end to end, the transmission systems to the distribution networks. This network of networks, as we know them, is aged, has not been maintained for a long time, and in fact, the investment continues to dwindle. So in other words, when we look at the demands that is placed on the grid as we know it today, is so much that we are not sure we'll be able to sustain the capability for this network to handle the demands at all levels. And by that, I mean that the demands in the generation continue to increase and is not able to meet the absolute need of today's need in terms of the different drivers, be it communication, be it all the new technologies that rely on the power subsystems. The network that is transmission subsystem equally is overloaded with a lot of demand, especially since the deregulation. We call it the open access. Becoming an open access means that I can add my power generation to the networks. And in doing so, the question is, therefore, how do we essentially determine whether its capability can sustain the new players? Finally, the distribution subsystems, as you know it, is where the customer end of things are. We need to turn the dishwasher on quickly. We consume energy in the homes. The appliances are not smart. They consume a lot of energy. Yet the cost of living continues to increase. So the big question facing all of us, therefore, is what can we do to make the grid of the future smart, to have the self-healing ability, to anticipate the demands that will be coming from different participants, in other words, different players. So overall, there are no regulations to open the market to make sure that we invest new technologies in these subsystems.
So there are several different points that you raised, and certainly the smart grid is exactly what you were just talking about. Dr. Anderson, then maybe turning to you, I know that in New York, you're working with Con Ed, the local utility there, and some of the smart grid technologies are already being put in place.
Yeah, we're trying to make it give a capability for the city to do twice as much work and transportation and enjoyment of life with the same amount of power. Mm-hmm. In order to do that, we're trying to create more of an internet-like system where we can route power from sources to sinks, what we call load pockets, mm-hmm. places where we have difficulty getting power to and from, and consequently we have to overpower the entire city. And we have excess power, so if we could make it more efficient using computer-aided systems, much like Google makes search engines more efficient, same mm-hmm. technology. We have high hopes mm-hmm. of being able to accomplish that task. So
the analogy is in the internet, you send an email out, and it may take different routes, but eventually it gets there as the packet of information gets where it needs to go. How does that work on the energy level? How does the analogy play out? In the electricity world, in the distribution side, the electrons slosh around to wherever the low spots in the, think of it as the ocean sloshing around. We distribute it into neighborhoods in New York that we call networks. And those networks are highly populated sometimes during the day. Mm-hmm. For instance, Manhattan has 8 million people in it during the day, and then at 5 p.m. they all distribute out into Bronx, Brooklyn, Queens. And the distribution of that power, right now we have to keep maximum power for both locations, mm-hmm. even though we only use it at 2 p.m. In Manhattan and at 8 p.m. in Brooklyn. Mm-hmm. So you'd want to be able to take that power and move it where it's needed at the right time. Just like the emails. Right. Ship the power to where it's needed, and therefore not have to have such an excess capacity in the system. Right. And that's part of the kind of power optimization, Dr. Moma, that you talk about, I assume.
Yes. The total optimization of the grid suggests that you are going to optimize your energy resources. From the generation point of view, there are new renewable energy that has to come in. The generation has to anticipate the demands on it. And you have to make sure that the new generations are so optimized that even the climate change issues is handled at that end. Beyond that, you now have the transmission subsystems, where you are trying to make sure you push power efficiently with minimum loss at optimal cost, affordable pricing. Therefore, to do that, you need a global optimization for that grid that anticipate problems and provide solutions. At the same time, optimize the control systems that will be allowable, that will allow you to push optimal power through. Given that, then you go to optimize the distribution subsystem. Mm-hmm. There again, you are trying to make sure the customer is taken care of. One, to make sure it's paying affordable prices. You have to ensure that energy loss is minimized. You also have to ensure that all of a sudden that the price signals are appropriate, in which case the price incentive to want to use less becomes a part of the equation in optimizing. So there are market issues. There are also tax credit that you have to give to people. There are barriers you have to overcome if you're trying to optimize the entire enterprise. Mm-hmm. And those barriers are, some are regulatory, some are the lack of investment, some are also lack of research, R&D support to make this happen. Again, the customer has a choice. It's part of the equation that you must put in as your constraint optimization. A little earlier, we were talking about the blackout of 2003, and I thought that would be a good example because this can be fairly abstract, the discussion of electricity and the grid. Can you take us through how that actually took place? I know that it was essentially a transmission level of problem, and what the smart grid, if the smart grid were in place the way you want it to be, how that would have been prevented.
Well, the main thing that happened for the 2003 blackout was that the problems in Cleveland were not being detected by the operators in Cleveland who were looking at their computers and not seeing any of the problems happening because of computer malfunction. And because they didn't know that things were going wrong, the disturbance cascaded right through Pennsylvania and New York and Ontario to put 50 million people out of without lights. So the main thing, of course, it started with the computer malfunction, and that's where the smart grid comes in, where you're not dependent on one area's computers to manage the whole grid. And the smart grid would make it more available to other operators, ways to correct the situation and take corrective action. So I think the smart grid at the transmission level would come in very much into play if we did that. Now, there were other ways of course, saving some of the distribution areas that would have also come into play if we had a lot more sensors and computer control on the distribution side as well.
Go ahead.
On that distribution side in New York, we were back in power in a couple of days. But one thing that it pointed out, it took us, after we got power established to the neighborhoods in the city, it took another 24 hours after that before the subways got up and running. And we realized that the electric economy of the future, where we're all headed, in which we're all going to have electric cars, we're going to have electric subways and trains, and we're going to have excess demand on the grid, we're going to have an integrated system that also has these other infrastructures in it. For example, water. 3 days worth of water supply in all of the vertical towers that people live in New York City, all of that water is pumped up with electric pumps. So after 3 days, we're out of lights, we're out of subway, and we're out of water. The sewers work, but the sewage doesn't get clean. And the natural gas is pumped also. So the infrastructure of the whole system needs to be understood by these computer systems of the future.
Actually, the distribution subsystem seems to be the low-hanging fruit, where we can easily incorporate some of the solutions that we have in building the future intelligent grid. In the sense that, at the distribution level, typically it's radial. And being radial, there are problems of restoration and so on and so forth to restore the system when power fails. What do you do, therefore, is to come up with some new embedded system of systems, which may involve communication subsystems like you had from Mr. Anderson, Dr. Anderson. An example, therefore, would be, do we have an automated function that will be able to, in my opinion, that will reconfigure the system? So we are looking for distribution functions for reconfiguration that will reconfigure the system, put the customer in the right loop of feeders so they can still get power at the right time, on time, just in time type of power. At the same time, you need to reconfigure system, you have to restore the system quickly. And to do that, you need some enabling intelligence systems that will allow you, by the intelligence systems, I'm saying the human ability to think, to solve problems in an automated fashion, rather than doing manual, knowing where the fault is in a feeder, for example. We can pinpoint the location of fault and remotely disengage some switches or turn on some switches or reestablish some customers, reconnect them at the appropriate time. Right. So you need a set of distribution function which involves even automatic billing, automatic metering, smart meters that will be able to tell, when a feeder is overloaded and so on and so forth. So it is indeed true that at the distribution subsystem, there are some quick fix that we could do that could also make this network very smart.
Beyond this quick fix really quickly, though, you have to be able to turn it into a smart machine. And a smart machine, more like a plane, is going to fix itself, or more like your car is going to have several computers that are predicting what's going to fail, not fixing it after it's failed, but predicting it before it fails so that you could keep the system up. And there we have peers from New York City's standpoint, for instance. Shanghai, London, Paris are headed to New York for a meeting next week where we talk about our integrated problems. And we find the same problems in all vertical integrated cities around the world.
Right. I'd like to talk more about that and certainly get to that customer level of the smart metering and what the future would feel like to somebody on the smart grid. So the question that you just brought up with smart metering and how the individual household can adjust the amount of electricity they use, I think is something would be really of a great deal of interest to investigate. And we actually have a piece of art, Josh, if we could pull up at the connected home of the future. But I'm interested in this, perhaps, Dr. Anderson, you could actually take us through what we're looking at. I mean, this obviously is a home that has advanced metering in place. And how does that work?
Well, everybody's familiar with Energy Star. Your appliances have a little star on, they're very efficient. We're starting to talk about within the electric economy of the future, what we're calling it with Con Ed the energy double star world, where the appliances are smart, they negotiate with each other without any human interaction, and in a large apartment building, for instance, the refrigerators will turn themselves off for an hour a day in sequence as they rotate around the apartment building. And then the other big problem we have is if we go to electric cars and everybody drives to work with an electric car and then plugs it in, we even have designs for plugging it into your parking meter in New York City. Mm-hmm. You suddenly load up the grid with massive amounts of additional draw that we'd like to dampen out. And in order to do that, you have to be able to introduce storage as well as generation. Alternative energies such as solar, wind, anything you can think of needs to be stored so that it can efficiently be delivered, not just delivered when the peak demand is. And that's the idea of this cartoon, is that you have everything communicating with each other without humans, negotiating using perhaps price signals to decide when one refrigerator makes a bid to another refrigerator. I really need to keep my beer cold, so I'm going to give you an extra $2 off your bill because I'm going to pay it for you. The other refrigerator says fine.
Right. And that's in response partly to the larger grid setting the signal saying, well, we're getting pretty close to a peak here. The situation's getting a little dodgy. Who's willing to reduce their demand?
Yeah, I think that makes sense. That is where we are looking at, when I said the low-hanging fruits, when I mean that there are some quick fix. What I really mean is that we have quick opportunity to make impact, to demonstrate the capability of this so-called smart grid. Our distributions of systems, you now have opportunity to say, okay, if I put a chip on all the appliances in homes, those chips will determine or enable us to find out how much power is needed by a dishwasher, for example, and when do you need to have it on or off.
Right.
By turning it off when you don't need it, you are saving energy. So the equivalent of that is that you are allowing us to balance the energy requirement from end to end. If I have limited generation at this point, then it is wise that a customer has participated in minimizing the energy required at homes. So by doing that, you are actually helping us to stabilize the network or the system itself. And that is where I said you can now provide a price incentive for those customers that are already cooperating so much to reduce the demand in their different homes. So if we're able to do that, we might be saving a lot of money, whereas generating company will have been trying to minimize loss. Customer, on the other hand, is helping me to reduce the demand. So it's a win-win in this case. And it is that kind of home that we're going to call intelligent homes of the future. They are smart in the sense that the energy required by all the appliances are controlled and communicated through a central box, like you have your Ethernet website, web page, and you can actually click and determine how much energy is used by each of the devices in a home. And remotely, therefore, you can shut down or turn on as you need. I'm saying the price saving from that should be sent back or should be part of the equation that we use to have a public perception of good public policy, in this case, with our customers.
Right. And one of the things that'll do, of course, is that if we can bring down peak demand at certain times, we can get a lot more stability in the grid without actually raising the generating capacity by a tremendous amount. And Dr. Bose, I thought I'd come back and ask you about that. I know that you focus on transmission of electricity. How does that same kind of concept work on the transmission level, which is going, of course, from the power plants down to the level of the local neighborhood or home?
Well, I think it's somewhat similar. That is, anytime you're doing intelligent grid, what you have two aspects of it. One is to sort of match the load to the generation and also make sure that you're doing it at the cheapest possible way. and saving money at it. But the other important thing that you cannot do today at all is the speed at which you can take corrective action. That is, when you have, at the transmission level, when you have cascading events, that could happen in milliseconds, and there is no way that the operator can react to do something and take corrective action after things have started cascading, whereas computers can. Computers and controls and so on. And so that's one of the major things that the transmission system has to focus on to avoid these cascading events that has occurred. And the cascading could happen because of just bad luck or a storm going through.
Just to be really clear, what kind of corrective action would be taken? What does that exactly mean? What would the grid do?
Well, for example, the simplest one to think of is that you could isolate parts of the grid that are in trouble to make sure that the problem doesn't cascade to the other parts. For example, that 2003 problem, it could have been contained into the Cleveland region alone, which would have been only a couple of million people rather than 50 million people in Canada and the US, which is what it did. And these new systems we're talking about can certainly do that.
We are still assuming that the transmission system of the future is going to be deterministic. I'm not thinking so. I'm assuming that there's going to be a lot of anticipation in terms of the demands. There's going to be, therefore, a need for a predictivity capability of the transmission system of the future to predict when storm is coming, to predict when there is overload, to predict the temperature change, to predict when the demands are going to be more than the design limits. Because power engineers currently have this idea of the limit can be plus or minus 10%. I say no, that is deterministic. But when you are looking at stochastic aspect, that means randomness in terms of what is possible to happen. A tool that is needed, therefore, is what I think we are being currently sponsored by the National Science Foundation under Dr. Webers, to look at this so-called dynamic optimization of the grid. This idea means the grid, the optimization strategy will predict, will anticipate. What if the load grow by, we predict for 90%, but it's already 110. Can you do it? Can you handle it? So this kind of enabler, this software embedded in smart devices that are schedulable, they are controllable with communication strategy, of course, is the real way to go in designing and deploying and demonstrating the future intelligent grid at this transmission system. That means you must have new paradigm of specification of intelligent softwares that are going to be anticipatory, predictive, and adapt to new situations.
I got a great example of that was in Texas a month ago. We now have a really significant portion of the ERCOT grid supplied by wind power. The wind stopped blowing after several days in which it had blown hugely. And what that happened, because the wind was contributing so much, power plants came offline to do maintenance. And then the wind stopped blowing. And they couldn't get the maintenance back on in time. That shows you the integration of a smart system that has to go beyond just the electric grid. We call it lean systems in other industries. The electric utility industry is not lean. It doesn't know what's happening at the transmission side, at the power plant maintenance level, when wind or solar farms are producing. That is very doable. It's being done in virtually every other major industry in the world right now.
Okay. And if I could just take a question, this is from Martin Schroeder, the American Public Transportation Association. And he's asking what steps are being taken to organize and inform major users like public transportation authorities running electric train systems and subways and how to prepare for the coming smart grid.
That's exactly what we're trying to do in New York, is get the MTA and the New York Power Authority and the Con Edison together in terms of computer systems, so that one knows the other. Each sees something different. The drawdown from the electric grid is seen as power on the subway trains, and all of that system those two systems were built completely independently. I mean, in the subway system in New York used to have its own power plants. Now they're using the integrated power system of New York State, all the way into Canada. And the visibility that's required from a computer sensing standpoint has to cross the boundaries that have been artificially set, actually, between Metropolitan Transport Authority, Metropolitan Power Authority, blah, blah, blah. It's a very interesting problem in terms of breaking down silos.
In addition, I think they should prepare for environmental problems.
Yes,
There's
sir.
a global change, a global climate change concern that we all have. When you are solving this power equation, this smart grid issue, we must not forget the need for environmental impact. So as we encourage new participants, like the Transportation Authority, they, of course, we will enjoy using them as a mobile power, portable power, because they already have it. So we might say, well, they might be connected to the grid when it's not being used, when the trains or the buses are not being used. That's one idea of these plug-in hybrids.
Another one is to give them carbon credits to the Transportation Authority for taking all those automobiles off the road. Taking money from transportation and moving it over into public transportation, a radical thought. You all know what Mayor Bloomberg is trying to do and what the City of London has already done. Those kind of dramatic changes in transportation patterns have direct effect not only on the environment but also on the electric grid.
We had one question.
Okay, go ahead.
I previously asked a question if we could see the graphic. This is Bob Wilson, Western Area Power DOE in Lakewood, Colorado, West Denver, where we're building a big transit system. But the question that came up is in the design of the smart grid, from my background as a former field engineer and holder of power system clearances, we got to think about the safety aspects for the general public and especially the electrical workers. How's that going to be incorporated in this very noble project?
Again, it's it's an industry where we still electrocute several workers per year in New York alone. You have to build the system so that the computer system, so that the humans who work in and around it know what's energized and what's not.
So you're saying that there's an increased danger because the grid is actually by itself, exactly what you're saying, sending power through certain lines or reducing power to other areas.
And you have to be able to make sure that the workers who are out there, that's the people that I'm mostly worried about. And the question was probably related to the public as well. We don't want to kill any subway riders.
Some of the increase in danger is actually being put into the system because we are allowing generation to be put into the distribution system, which allows power to flow in the other direction than it normally does. And that has put in a lot of new ideas now into how to protect the system and the people who work on that system. This is a big question because what it means is that the technicians and so on that work on the system have to be trained differently than they used to be in the past. So this is partly because of the intelligence being put into the system and partly because we're putting more distributed generation on the system at the other end of the line.
If I could just ask you, Dr. Bose, you're talking about distributed generation, which is actually the kind of idea that certainly Popular Mechanics we've written about several times, and just sounds like a great idea. Could you explain to people who might not know just what that is and what the benefits are, what sort of the goal of distributed generation is?
Well, the distributed generation would mean that if you have a large number of wind turbines instead of concentrated in a wind farm, is to spread that around in a larger area connected to different points. Okay, a simpler example would be if a lot of us bought electric plug-in cars, we could use those to actually supply the grid during the time when there's a shortage of power from the generating stations. So that now you're plugging it into your home, whereas instead of the electricity coming from the electric company into your home, now you're supplying power into the grid. And that's what I meant by distributed generation and the electricity flowing in the other direction than it normally does. And that means that the whole design pattern of the distribution system, and this is what I think Roger was referring to, has to be now much more protected by computers and other devices from the system itself, as well as endangering any of the people on the other end.
Go ahead, sir.
Hi there. This is Imre Duke, Department of Energy. We have, of course, a very vigorous research program in smart grid technology, and we fund a lot of work. But we realize that you need an analog counterpart to the digital part. And what we need is not only distributed intelligence, but, as was mentioned, distributed generation and distributed storage.
Storage, yes.
In particular, the storage, which provides the buffer that will make all of this work much, much better. It's fine to say, you know, the electronics will respond instantaneously, but with a buffer, it'll work even better.
Yes. That's absolutely correct. Every big computer server farm, or even small one these days, has a universal power storage to accommodate the blinking. In Paris, for instance, they allow blinking. They have so much support of their computer systems. It has to be extended to the house, to the home, the basement of apartment buildings, subway system having batteries and storage. The storage is really critical to pulling off the distributed generation.
The question original was the safety issue. And I thought I should coin one more S, which is the security of the system itself. Whereas we develop new technologies such as the distributed generation or resources. There are issues of safety with regard to the protection schemes. And therefore, I think immediate technology that will be needed will be control technology, just to be able to detect the malfunction of these devices and provide corrective measures in a timely fashion. Security, of course, also take us to the overall security of this new system we are talking about. Security against enemy, against attack. Because there's going to be a lot of communication system embedded in the electricity system. So what does that mean with respect to virus, with respect to cyber attack? Are we going to be safe? So safe has two meanings for me. Safety in terms of being electrocuted. Safe in terms of you put this out there and you have not educated the customers properly. So my third alphabet is therefore satisfaction, customer satisfaction in the process of all this.
Right.
How much will it really cost to do or to put this together? So yes, we need to include storage. We need to include distributed generation of all types. I'll give you one example just to close this gap. The wind energy type. Sure, it's one of the DG options called distributed generation option. But then it's based on the speed. And what if you design this wind energy source and the speed goes out of order? Before you know it, the thing rotates at an abnormal speed. What you find very quickly is that it could just fly out of the region of your region of interest, of safety, and it could easily hurt a lot of people. So we need to detect, we need to design a control strategy that will even monitor the speed of your distributed generation to be sure it's within safe limit. And I can give you an example of all the DG options, how you have to make sure you protect them and anticipate problems before they occur. Always anticipate it, not after the fact.
I have a question at a larger scale. Given that we have facilities, infrastructure in place that we can use more efficiently, prolong its life, get more benefits from it, we still have to invest in enough infrastructure to provide reliability at the catastrophic scale. That is, extraordinarily large power demands for short periods of time, storms that take things out. It's generally not in the economic interest of any particular utility or any particular individual to provide that kind of reliability. doesn't make economic sense, but we as a society need that reliability. What kind of a regulatory framework would you guys propose to take care of that problem?
If I were to answer the question, what do we do first in building this smart grid? You have to get your regulations right. You have to get your standards right. It will be a waste of time and effort if we don't agree on what the standards should be. Because I'll be building my own intelligence subsystems technology for intelligence grid, but nobody uses it at the end of the day because you're building yours, I'm building mine, and they're not compatible. So the first step is to make sure we have legislation, regulation, public policy, public awareness, public education, to make sure that we all agree in terms of the framework on which we're going to build the different technologies that is going to be embedded or enhance the existing legacy system to make them smart. Obviously, we're not going to throw what we have away. We're going to embed through software, intelligent software schemes. We're going to put in some intelligent devices. We're going to add some added value of communication systems. We're going to use human capacity. Overall, you're going to regulate, but you've got to also ask legislation to pass to support research that will make this happen. Otherwise, we'll be talking all day long, but there's no money to back it up. We need the human intelligence as well as the grid intelligence to converge at one time to solve this problem. And it's now that it has to start at the same time. There are short-time goals. There is a mid-time goal. There's a long-time goal that we have in building this. We're not trying to build intelligent grid by tomorrow. We're saying that in the next 5 years, what are we going to do? What can be reachable? Then we look at another 10-year span, then another 15, 20-year span. I'm suggesting that by 2020, what is our vision? Vision in technology development, in support of generation, transmission, distribution subsystems, vision for the operational support for the system, the planning horizon, planning over 100 years, of course. Then you have to look at the regulation. And, of course, the people, the culture also have to come in. We would like to sustain the quality of life as we know it. That is why we are supporting the idea of resiliency of the network, sustainability of the network, because we feel that our lifestyle has come to be so good, and we depend on the resources, on the energy and the resource constraints that comes with it. Be telecommunication, be water, be transportation, be people, and we must sustain this. Hence, renewable energy will be one of the elements to make it happen. The smart homes will be one of the elements, one of the subsystems that we must put together to make it happen. Right. Of course, I'm thinking that tomorrow I can walk to a Best Buy and pick up something to make my home smart, save my energy. My wife pays the energy bill. Maybe she may want to reduce the bill tomorrow.
I think the reliability of the grid being a public good is an interesting question because we in the U.S. Have a slightly different structure of the power grid than they do in most other countries, which is government-owned, and they actually in other countries can determine the reliability for which we are willing to pay. Here, because private companies have to come in, the way we have to make sure that the reliability is there for the public good is by standardization and by regulatory moves. And that makes it much more interesting because the way utilities and power companies recover their investment is through rate regulation by states. So we have a round-robin problem in this country which requires sort of a high-level look at how to make sure that the right amount of reliability is built into the grid for the public good that we think is necessary.
I have a question, and maybe Dr. Bowes, you can help us get at that. Reliability of the grid would have to do with a number of different elements, but certainly demand is likely to rise. How much can be done in terms of a smart grid technology, and to what extent do we just need to build more transmission lines and more power plants? I mean, I think the country now uses about 4 trillion kilowatt hours of electricity each year, and that number is likely to rise. So how do you balance the various ways we have of increasing reliability?
Yeah, another way to look at that statistics is 40% of all energy consumed in the United States is actually turned into electricity. So that we consume it as electricity. The interesting thing that we have to point out is we can put a tremendous amounts of intelligence onto the system, which consists of computers, control, and communications. None of that produces any energy or transmit any energy. So ultimately, the reliability of the grid fundamentally has to be met by building more generation and transmission and distribution to meet the power demand or the energy demand of the country. What we do by increasing the intelligence of the grid is better optimization, better economic benefits, better reliability. So we are taking what we have as an infrastructure, which has to be the basis of the reliability, and then trying to squeeze the last element out of that by doing it intelligently.
Right. I know, Dr. Anderson, you have some ideas about how much we can increase the transmission capacity in places like New York.
Well, it's think of the 40% number for now.
Mm-hmm.
What will it be in 20 years, 30 years? We believe it will be 80% is turned into electricity. That's what we talk about when we say the electric economy. And you just cannot put that much wire in the ground. All of ours in New York City is underground, and we have the largest copper mine in the world already in our streets. We're running out of room. So hopefully we can figure out how to transmit it more efficiently and do more work with less electricity. That means efficiency. That's what efficiency is. And that's why we keep casting our glances at leaner industries that do just that. The airplane, the 787, is going to fly on half the fuel that the 777 flew.
Assuming they get it built.
Assuming they ever get it in the air. Right. They will.
We have another question from the audience here.
There are a lot of national issues at stake here. As a consumer, I have to confess, the rising cost of electricity and the environmental effects with the CO2 are the things that really worry me. The other things seem pretty small compared to that. I look at the way our natural gas bills have been going up, and my electricity bills for the daytime are going up because we have to import natural gas more and more because of these little natural gas generators they're building in the big cities. That takes us back to what you guys were saying earlier, that renewable energy is an essential part of what we need to do. And then, as you said, we need storage for renewable energy or for other reasons, because if the wind blows sometimes and not others, we better be able to store it if we want to be able to use it. But there's a big hole in the discussion. The old way of running the power grid that 90% of the experts still do today is some combination of local little algorithms that don't know the big picture, human operators that get mixed up and lead us to blackout sometimes because they don't know how to cope with the information, and automated systems. The only automated systems I know of today to do this optimization of power flow is the optimal power flow kind of algorithm that Jim Momo here has developed. Okay? He's made it real. But the problem is what we have today is static. It gives you the best power flow today. But if you want to use storage, you can't use storage efficiently unless you have a new kind of intelligence. It's not enough to have a lot of computers. It's not enough to give contracts to people who do it the old way. You need to extend these kinds of algorithms to be able to handle the problem of anticipation and time shifting. And that's where there's some new mathematics coming online, but it's going to take a major paradigm shift because most of the world isn't doing it yet. And that's a big part of the struggle to get beyond words about intelligence to making it really real.
All right, Dr. Anderson, maybe you can discuss that.
Yeah, even in the energy business, refineries and liquid natural gas facilities have to see the market in the future. They build their economic optimization based on profitability. and they have to see the future. The future also includes weather and all of these uncertainties. There are total plant software systems right now running virtually all of the high-tech refineries and petrochemical plants in the world. That would be the envy of the electricity industry. It's not that the optimization problem is not seeing the future. It's that the electric optimization problem is not seeing the future yet.
Now, you do have some predictive software in that Con Ed.
Yep, that's right.
Maybe you could talk about
and where did it come from? It came from developments in other industries.
Mm-hmm.
I mean...
And the idea there, just to elaborate on what, I saw Dr. Anderson was kind of showing me around a grid control center in New York. You're there trying to at least predict what might fail so that repairs can be made in advance. Maybe you could describe how that works.
Yeah, so every system in mechanical factories and machinery in general know about sensing vibration and wear and tear. Jet engines go in for repair basically by calling home themselves and saying, I'm not quite feeling right, I need to have somebody look at me. A car does that. The electric grid has a lot of the sensors, has a lot of the autopsies done on the failed systems so that you can develop failure models of the components, like a transformer or a feeder or anything in the system. What it doesn't have is the system integration that understands the plane crash as opposed to the equipment failure. So a plane doesn't crash anymore because of one system failure or two system failures. It takes three, three or more. Three will take a plane down, even though you have redundant systems in each of those three. And in order to build that integration of those odds of failure, you have to have a really good solid model of how the system works. Toyota built the better Lexus by building a model of the Lexus. And only after they had the car model in the computer could they build the optimal car for Toyota. We're struggling with building that optimal model for New York City, for example. There are 5 million nodes, 5 million connection points to the electric grid just inside the city limits alone. And we don't even have it connected to the transmission grid. Those are massive computational problems, but they're not insurmountable. They're simply not.
Go ahead.
I'd like to just add a little comment on the issue of the need for advanced strategies, which we have been referring to as optimization. In fact, in the energy bill signed by the President in December, it was a bullet item. There is a need for dynamic optimization. If you pay attention to what one of the panel audience said, that we do need a global, adaptive, stochastic optimization of the grid. It has to be funded. There are only a few people who want to do this kind of work, because some of our colleagues are used to the old traditional optimization, which I myself participated in. And they want to keep this. They don't want to take new risk. They don't want to fund new ideas. And I think this is the first step we must take. Because in doing that, this new technique will be able to look into the future. We'll have anticipation for what if the change in the flows in the network suddenly increase. Are we ready for it? What if the population demands for power changes erratically? We don't know what they will be asking for. We don't really know what the customers have out there. We know they are all using all kinds of gadgets now. Then we also have to ask, what if the source of energy itself dwindles or suddenly changes its pattern? Mind you now, we don't even know the color of power we have. The electricity has no color. It's just coming. We don't even know whose power we are using in the old system. So if you're developing a tool, you have to think carefully that will my tool be able to have this predictability? And the ability to do that is perhaps education also. You need to fund researchers, students of the future, whose mindset is about new things. Just like you said, in the auto industry. If I go to see my doctor, he has a small history of my family history, of my health history. He can predict how long I will live, maybe, what type of medicine I should take, maybe, to sustain my life. This is the type of remedy we don't have. I call it remedy for detection. I call it remedy for prevention. So in the different subsystem of power, whether it be in the generation system, this new thinking has to be there. In fact, the word smart means taking my human ability to predict, to think, and put it in systems that don't talk before, that looks just silent, but doing wonders. The generations only hum, make noise. That's all they do. They don't think. But can we make them think to anticipate what is going to happen? You can now also bring in an optimizer that optimizes the energy usage and also optimizes the reliability you are looking for. You all talked about reliability earlier. By the way, there is what I would call societal acceptable reliability. What is that definition? In other parts of the world, they take it for granted that, well, you can have power failure on every day, on a given day of the week.
Right.
But then it's because society allows it. In the US, we are defining reliability. It's not just a number. It has so many parameters. It has a GDP issue with it. It has the population, the region where you live, in defining what I call your reliability. Right. So by definition, we are coining at Howard University a new definition of reliability. It's not just expected unserved energy anymore. It's societal expected unserved energy. That, I think, is New York way.
If I just want to see if there's one more question in the audience. We'll just need to get you microphone. Oh, you have it. Great.
Microphone. Okay. My name is Lamine Milly. I'm professor of power at Virginia Tech. I would like just to argue a little bit about the capability to predict failures in a system like the power system, which is extremely large scale, continental scale, which make it different from, let's say, an airplane or a car. We don't have hundreds of thousands of components here. We have millions of components distributed over large scale areas. To make the system resilient, and I'm going to make a difference between resiliency and reliability. They are very different. Reliability, effectively, you build reliability through redundancy, and I totally agree with the panel on that. Resiliency is very different. To make the system be able to respond extremely fast in a time constant, as Ajahn Bose said, in few milliseconds, to eventually unpredicted failure. That means that no matter what your capability of intelligence and predictability, you cannot predict all failures. There are some failures that are unpredictable, and you have to face that possibility. There is a risk there. The risk cannot be zero. Okay, there is a risk, so you need to make the system agile, and for that you need to have distributed, coordinated control. What is missing today in power system, we have distributed protection systems that are not so well coordinated. You need to coordinate those actions, and in addition, you need to put the load in the picture. The load can contribute in a very effective manner to make the system resilient to cascading failure.
Dr. Bose, maybe we can turn to you. You might have a response to that. And also, I want to make sure that we have any final comments that you think we should walk away from here with.
Well, I thought that it was interesting. The last two comments from Professor Milly and Professor Momo were pointing to the fact that there are questions that need to be resolved by doing a lot more research and development. And one of the issues I think we should leave with is that research and development in the power grid has been tremendously lacking in the United States in terms of the amount of money you would expect that would be spent on something that is a $100 billion industry that we're looking at. So that's one thing. The added, because there hasn't been much research and development, there has been also an issue about where the new people are going to come from into this industry who are going to solve these problems, who are going to build the intelligence into this. We're not training enough engineers and scientists and people and even technicians who can do this work. And these are major issues that we have to face. We can talk forever about how intelligent this system ought to be and how reliable it ought to be, but it's not going to happen if we don't solve some of the other infrastructural problems, which has to do with people and education and research.
Thank you very much, Dr. Bose. I also want to thank you before we end for participating very much. And that's actually almost a perfect comment for us to close with, because a part of the mission, of course, of Department of Mechanics and certainly National Science Foundation is to encourage the best ideas and the smartest people to go into solving the country's problems. And that's something that we're all engaged with here, and certainly we have on the panel with us educators who are dedicated to doing exactly that. I want to thank you also both very much for being here. So thank you very much. Once again, this is Jerry Beilinson for Popular Mechanics and the National Science Foundation. Thank you.
Thank you.